Every single second, there's a nuclear furnace 93 million miles away from us that unleashes more energy than all of humanity has used in its entire history. And that's not some sci-fi concept. It's the star right at the center of our solar system. So today, we're going to take a journey to really get to know our local star, the sun. Okay, let's just start with a number that is almost impossible to wrap your head around. 4 times 10 to the 26 watts. I mean, that number is so huge that the entire energy use of our whole civilization is just a tiny, tiny blip compared to what the sun cranks out in a single second. It's just a truly staggering amount of power. And that power leads us to the big mystery, the one that had scientists scratching their heads for centuries. You see, the sun is ancient. It's been burning this brightly for 4.5 billion years. So the big question is, how? I mean, what kind of fuel could possibly last that long? That's the puzzle we are going to solve together. So here's our game plan. We're going to start with the sun's unbelievable size. Then we'll take a tour of its wild, layered atmosphere. After that, we'll dive into the magnetic storms that cook up solar weather, and then we journey deep, deep into the core to find the secret to all that power. And finally, we'll bring it all back home and see how this connects directly to us, right here on Earth. Okay, first things first. To really get a feel for the sun, we have to grasp its colossal power and, what it's actually made of. So to get a sense of its scale, picture this. If our Earth was just a single grain of sand, the sun would be a beach ball. Yeah, you could cram 1.3 million Earths inside of it. And it's not a solid rock like our world. It's a giant ball of superheated gas we call plasma, a state of matter that's so incredibly hot, atoms are literally ripped apart. Now, what's so fascinating is how simple the sun's recipe is. It's about 73% hydrogen and 25% helium. And everything else, the carbon in your body, the oxygen you're breathing, the iron in your blood, all of that is packed into that tiny little 2% slice. In a very real way, we are literally made of stardust. And this is where you can really see just how different the sun is from our home planet. Earth's crust is all about heavier elements like oxygen and silicon. But the sun's simple, hydrogen-heavy makeup, that's actually way more typical of what the rest of the universe looks like. Our walky little planet is the odd one out. All right, let's move on to our next stop. We're going to take a tour of the sun's atmosphere, starting with the part that we can actually see. So this is the photosphere. Now, it's not a solid surface you could stand on or anything. It's really the layer where the gas becomes so dense we can't see through it anymore. And that mottled look it has, what we call granulation, well, that's caused by these giant bubbles of hot gas rising up, cooling off, and sinking back down. It looks a lot like a giant pot of boiling oatmeal. Just above that is the chromosphere, which means color sphere, and it gets its name from its reddish glow. And this is where things start to get, well, weird. At about 10,000 Kelvin, the chromosphere is actually hotter than the photosphere right below it. That's the complete opposite of what you'd expect. It's like feeling the air get warmer as you walk away from a campfire. And the mystery just gets deeper when we get to the corona. This is the sun's wispy, ghostly outer atmosphere that you can see during a total solar eclipse. It stretches for millions of kilometers out into space, and its temperature is an absolutely mind-blowing 1 million Kelvin or even more. How the sun heats its outer atmosphere to these insane temperatures is still one of the biggest puzzles in astrophysics today. So all that intense, mysterious heat and energy, it's what drives the sun's incredibly turbulent weather, and it is all powered by one thing: magnetism. You see, the sun's activity isn't constant. It actually ebbs and flows in this pretty predictable rhythm we call the 11-year sunspot cycle. During a solar minimum, the sun is pretty chill. But as we get closer to a solar maximum, like right now in 2024 and 2025, its surface gets covered in sunspots, and activity just ramps way up. So, what's causing this cycle? Well, it's all about how the sun spins. Since it's a giant ball of gas, its middle, the equator, spins a lot faster than its poles. This twisting motion stretches and tangles the sun's magnetic field lines, kind of like twisting up rubber bands. And eventually, when they get too tangled, they snap and burst right through the surface, creating those active regions we see as sunspots. And these active regions are where all the action is. Sunspots are like the anchor points, and from them, we see these giant, beautiful loops of gas called prominences. But when those magnetic field lines finally snap, they can unleash solar flares. These are just immense bursts of radiation and sometimes even coronal mass ejections, or CMEs, which are these colossal clouds of plasma that get shot out into the solar system. All of this violent magnetic weather we just looked at, it's really just a symptom. To understand the engine that's driving it all and to finally solve our 4.5 billion-year-old mystery, we have to go past the surface, right to the true source. We are going to the core. And the key, the one thing that unlocked this whole puzzle, came from Albert Einstein. His famous equation, E equals mc squared, it revealed a shocking truth. Mass and energy are really just two sides of the same coin. Mass itself is a form of super-concentrated energy, and it can be released. And that is the principle behind nuclear fusion, the engine that powers the sun. So imagine smashing two small Lego bricks together so hard that they fuse into a single, slightly smaller brick. That little bit of leftover dust, that tiny missing piece, becomes a huge burst of pure energy. That's exactly what's happening in the sun's core, but with atoms, and on a scale that is just unimaginable. The sun's fuel is hydrogen. Down in its core, the crushing pressure and intense heat force hydrogen atoms to fuse together, and they create helium. Now, here's the crucial part. The final helium atom that comes out weighs just a tiny bit less than the hydrogen atoms that went in. That lost mass isn't gone. It's been converted into a massive amount of energy. This process, happening trillions of times every second, is the real secret to the sun's incredible, long-lasting power. So, we've solved the mystery. But the story doesn't just end in the sun's core. Oh no, that energy travels outward and it directly impacts us right here on Earth. The sun doesn't just send us light and heat. It's also constantly breathing out this stream of charged particles. We're talking mostly protons and electrons, called the solar wind. It flows out from the corona and travels at nearly 1,000,000 miles per hour, bathing the entire solar system in this constant flow from our star. And the way this solar wind, and even bigger events like CMEs, interacts with our planet is what we call space weather. Now, when these particles hit Earth's magnetic field, they can create the beautiful auroras. But more intense storms, they are a real threat. They can mess with the GPS in your phone, interfere with airline communications, and even damage the satellites that power our modern world. In really extreme cases, they can cause widespread power blackouts right here on the ground. And this all leaves us with a final thought to chew on. The sun has this duality. It's the source of all life on Earth, right? The steady, reliable heart of our solar system. But at the same time, it's a turbulent, magnetic star whose violent outbursts could seriously disrupt our modern, technology-dependent lives. So as we head into another period of peak solar activity, it really forces us to ask, are we actually prepared for whatever our star might decide to send our way?